Neural networks power almost everything we call AI today. They recognize faces on your phone, translate languages, recommend videos, and even generate images and text. But most explanations make them sound insanely complicated, full of equations, jargon, and diagrams only experts understand. The truth is much simpler. A neural network is just a pile of tiny mathematical steps stacked together until patterns begin to form. And once you understand the basic idea behind those steps, the whole concept suddenly becomes clear. In this video, we're going to break neural networks down in the simplest possible way using visuals and everyday logic. No math, no jargon. Just a clean explanation of how millions of small operations add up to something that looks like intelligence. Let's get started. What if I told you that the technology behind voice recognition image generation, face unlock translation, and even ChatGPT all comes from the same simple idea, a network made of tiny mathematical switches? Neural networks sound complicated, but once you see the core idea, everything becomes clear. They don't think like humans. They don't understand like humans. They simply take input, transform it through many small steps, and produce an output. And when you chain enough of these steps together, something that looks like intelligence begins to emerge. Today, we're going to break neural networks down in the simplest way possible. No jargon, no equations, just clear explanations and intuitive examples that reveal how machines learn patterns. Let's begin with the basic question: what is a neural network? At its core, a neural network is a system made of many small units called neurons. But these neurons are not biological cells. They are tiny mathematical functions. You can think of each neuron as a simple calculator with one job: take numbers and combine them. Apply a small rule and send a number out. One neuron alone can't do much. But when you connect thousands or millions of them together, layer after layer patterns begin to emerge. Patterns that allow the system to classify images, recognize speech, translate languages, recommend videos, and generate text. So why do we call them neural networks? Because the idea was inspired by the human brain. Biological neurons receive signals, process them, and pass signals forward. Artificial neurons do something similar, but in a much simpler way. A biological neuron is full of chemistry, electricity, and complexity. An artificial neuron is just math. But the inspiration is the same. Many simple units connected create powerful behavior. To understand how a neural network works, imagine the simplest possible structure. You start with an input layer. This is where the data goes in. If you want to recognize handwritten digits, the input layer receives pixel values from the image. If you want to classify an email, the input layer receives features extracted from the text. If you want to translate a sentence, the input layer receives the encoded tokens. Then comes the hidden layer, the real engine of the network. Hidden layers transform the data step by step. Each layer takes the output of the previous layer, applies its own calculations, and passes the result forward. Finally, there is the output layer, the result. For a digit classifier, the output might be probabilities for the numbers 0 through 9. For translation, the output might be the next word in another language. This structure gives neural networks their power. But the real magic lies in the connections between the neurons, the weights. Every connection in a neural network has a weight attached to it. You can think of a weight as the importance of that connection. If the weight is strong, the signal is amplified. If the weight is weak, the signal is reduced. And during training, the network adjusts these weights again and again to reduce errors. Imagine a giant network of knobs and sliders. During training, the network slowly turns those knobs until it gets better at the task. The final arrangement of weights is what the model has learned. So how does a neuron actually work? Each neuron receives numbers from the previous layer. It multiplies each number by its weight, adds them together, and then applies something called an activation function. You don't need to know the math. Just think of the activation as a decision gate. If the combined signal is strong enough, the neuron activates. If not, it stays quiet. This simple mechanism, multiply, add, activate, is repeated millions of times across the network. Now let's walk through the process called the forward pass. The forward pass is when data flows from the input through the hidden layers and finally to the output. If you give the network an image of a cat, the forward pass pushes the pixel values through all the layers until the output says something like cat 0.93. That means the network predicts a 93% chance that the image contains a cat. But the first time the network runs, it will be terrible. It doesn't know anything yet. It produces random outputs because the weights are random. That's where learning comes in. To learn a neural network needs a way to measure how wrong it is. This is where the loss function comes in. The loss function compares the network's prediction with the correct answer. If the network predicted cat but the image is actually a dog, the loss is high. If it predicted correctly, the loss is low. The goal of training is simple: minimize the loss. So how does the network reduce its errors? Through a process called backpropagation. Backpropagation is the method the network uses to learn from mistakes. After the forward pass and the loss calculation, the network works backward, layer by layer, adjusting the weights slightly to make future predictions more accurate. You don't need to understand the math behind backpropagation. What matters is the idea the network nudges its weights in the right direction. Do this millions of times, and the network becomes surprisingly good at recognizing patterns. Think of backpropagation like practicing a skill. When you first learn to play piano, you hit wrong notes. Each mistake teaches you something. Over many repetitions, the mistakes shrink and the performance improves. Neural networks follow the same principle. Now let's talk about training versus inference. Training is when the neural network learns. It sees many examples, compares predictions with correct answers, measures loss, and updates weights. This process is slow and computationally expensive. It might require powerful GPUs or specialized hardware. Inference is when the network uses what it has learned. When you take a photo with your phone and it identifies faces in less than a second, that's inference. When you speak to a voice assistant and it understands you, inference. When you ask an AI model to write a poem, inference. Training is the long journey. Inference is applying the result. Now let's talk about deep learning. Deep learning is simply the idea of using many layers. The more layers a network has, the deeper it is. Deep networks can learn more complex patterns because each layer builds on the previous one. In image recognition, early layers might detect edges. Middle layers might detect shapes. Later layers might detect objects like eyes, noses, or wheels. Final layers combine all of those pieces to identify what's in the image. This layered structure lets neural networks break complex problems into simple steps. Now, the big question: why are neural networks so useful? Because so many things in life involve patterns. Speech has patterns. Images have patterns. Text has patterns. Behavior has patterns. Neural networks are incredibly good at finding patterns, even ones too subtle for humans to notice. This is why neural networks show up everywhere in your daily life. When your phone recognizes your face, neural network. When YouTube recommends a video, neural network. When your email filters spam, neural network. When Google Translate converts languages, neural network. When AI creates images or writes stories, neural network. When self-driving cars detect pedestrians, neural network. They have become the foundation of modern AI. But like all tools, they have strengths and limitations. Let's start with strengths. Neural networks can learn incredibly fast compared to humans. They can analyze massive datasets. They can detect patterns impossible to see manually. They can generate new content, images, text, audio that feels creative. But they also have weaknesses. Neural networks require large amounts of data. They can be biased if their data is biased. They can make mistakes that are surprising or strange. They sometimes produce hallucinations or overconfident errors. And they're often black boxes, meaning it's hard to explain exactly why they made a specific decision. Another important point: neural networks do not have consciousness. They do not think or feel. They do not understand the world the way humans do. They do not have intentions. They do not know if what they produce is right or wrong. They only follow patterns learned from data. Even when a neural network recognizes a cat, it doesn't know what a cat is. It only knows that certain patterns of pixels often lead to the label cat. Now let's bring all the pieces together. A neural network receives input data. It passes the data through many layers of neurons. Each neuron applies simple mathematical steps. The network measures how wrong it is using a loss function. It adjusts the weights through backpropagation. Over time, it becomes better and better at its task. During inference, it applies what it learned instantly. And when it has many layers, it can solve very complex problems. Millions of tiny adjustments turn into powerful intelligence-like behavior. The big idea is simple. Many small operations, when combined, create something that looks smart. Neural networks are not magic. They are not brains. They are tools, powerful ones, built on simple rules, scaled to enormous size. And now that you understand how they work at a fundamental level, the technology becomes far less mysterious. You can see why they are so powerful, why they sometimes fail, why they transform industries, and why they are at the heart of modern AI. Neural networks show us a fascinating truth. You don't need a brain to create intelligence-like behavior. You just need patterns, adjustments, and enough simple pieces working together. That's the simple story behind neural networks explained for beginners, with clarity, intuition, and no jargon. Neural networks aren't magic, and they aren't miniature brains. They're systems made of simple pieces, each doing almost nothing on its own, but working together in a way that creates surprisingly intelligent behavior. And once you understand how they take inputs, transform them, measure mistakes, and adjust, the entire field of AI becomes far less mysterious. Whether you're learning AI for school, for work, or just out of curiosity, knowing the basics of neural networks gives you a foundation for understanding everything else. Deep learning, image recognition, language models, and even the future of artificial intelligence. If you enjoyed this plain explanation and want more videos that make complex ideas feel simple and visual, feel free to subscribe and continue exploring with us. Until next time, stay curious, because the future is built from understanding one idea at a time.